So assuming that it's not any worse ending up in Texas than it is ending up in California, which is a difficult assumption, I understand. See, there are more people in California than there are in Texas, so I have to. So my loss of insulting Texas is lower than my loss of insulting never mind. Okay, getting back to this. So I know what my losses are. The thing that I don't know is the probabilities, right? For a given x, how do I actually know what the probability is that it's a 4? I have to somehow learn that or know that. So who's going to help me? Whenever we do recognition machine learning, what's going to help me? It's the data. The data are the first thing that's going to help me. There's somebody else that's going to help me. I'm going to bring them along in a minute. So here we have some images of pictures, and as you can see in the red circles, there are some pixels that are from, say, skin, and there are pixels that are not from skin. And let's suppose I just want to label a pixel or a little patch as, is that skin or is there not skin? By the way, this is a cute little thing for those of you out there. We did a bunch of skin detection, et cetera, and in Sandy Pentland's lab, and I think Thad Starner was involved back when he was a student, it turns out the color of skin is pretty constant. The luminance changes, right? So some people, you may have noticed, are darker than other people. But they're darker, they just have more of the same pigment, right? The melanin pigment. So when you look at skin in a color space, if you remove the illuminant, it's actually possible to detect skin for a very wide range of how dark the skin is using the same color, removing the illuminant. Now you have to worry about lighting and a bunch of other things. But it makes sense, right? Because there's only one pigment. Anyway, we're going back, we're looking at skin color. There's a bunch of pixels that are skin color and a bunch of pixels are not. So what am I going to do? Well, what I do is I'm going to take the skin pixels, all the pixels that somebody supervised, remember supervised learning, have classified as being skin pixels. And I'm going to build a little histogram of their feature. Now, the feature that we're using here is hue. Hue is essentially the color with the amount of brightness and saturation removed. It's, you know, how red, greenish, bluish, yellowish is the color. And what this is this is a little box that's essentially the percentage. It's a histogram. That's the percentage of pixels, of the skin pixels, that have this hue. And a histogram is an approximation to the probability distribution. But notice that it's the probability of getting that particular hue given that it's skin. It is not the probability that it's skin given these hues. Okay? This is remember the likelihood? All right? Well, what do I do after I've done the skin pixels? Well, I do the not skin pixels. I build another graph, right? And in fact, what's interesting is you'll notice there's a little bit of overlap here, right? That's not too surprising. There are some, in fact, in real life, there actually would have been some down here too, et cetera, whatever. Because, you know, there are skin-colored pixels in the non-skin world, okay? And there are some skin that, you know, people go and get tattooed or something. I don't know, whatever. You know, but in general, I'm not going to have a clean separation, but I'm going to have a distribution that hopefully has some differences between them. And again, this is the probability of getting that hue given that it's not skin, and it's not the probability the other way around. So all we have at the moment is the probability of getting a hue given that it's skin, probability of getting a hue given it's not skin. But what do we really want to do? Well, somebody gives us a picture. This is a stunning picture of the Beatles, actually. I've never seen this picture before. Well, that's not totally true. I saw it the last time I gave this lecture, but you know what I mean. Anyway, we get in a new picture, and what we want to do is we want to label each pixel as being skin or not skin. Or more precisely, we want to know the probability that it's skin or not skin given, say, some of the color. So, do I have the probability that something's skin given its hue on this slide? Megan, do I have it? Yes.
Yes.
Wrong. No, I have the probability of a hue given that it's skin, right? What do we have to do? Well, you've all seen this coming. Where else do I get help from besides the data? I get help from Dr. Thomas Bayes, okay? Bayes' rule, remember Bayes' rule? We did Bayes' rule now a couple of times. Bayes' rule says that the probability that it's skin given X, and that's referred to as the posterior, can be written as a prior. If I pull out some pixel and I don't tell you anything about it, what's the probability it's skin? That's the prior. And I multiply that by the likelihood, P of X, given that it is skin. Now, that we do have. Remember those histograms? That's the probability of getting a hue given that it's skin, so that we have from the data, all right? But the prior is added in here. And in fact, if we remove, since we've got our measurement, we can sort of pull that out. We did that last time for our particle filtering, actually. We can say that the probability that something is skin given a measurement is the likelihood, or is proportional to the likelihood times the prior, which all brings us to the question of where do you get your prior from? Okay? We've run into this problem before, and we told you to go to get in your car, drive to Greece, go to the Oracle, get a prior. Well, that's one thing you could do, but airfare to Greece is expensive. So we have to do something else. And Steve Seitz wrote this Bayes rule in use/abuse. It was kind of cute. I kept the joke. Thanks, Steve.
Okay, let's see if we understand the issue here. We already have two histograms. One that gives us the probability that an observed hue value is from a skin pixel, and another capturing the probability distribution of it not being a skin pixel. Now along comes a pixel whose hue value lies somewhere here. Say this corresponds to bin value 6. Using this, we can find out the bin heights or corresponding probabilities. Let's say that the probability that this value came from a skin pixel is 0.5 and that it came from a non-skin pixel is 0.1. Okay, now that you have these two values, can you decide whether x came from a skin pixel or not? In general, is this condition sufficient? That is, I'll say that x is a skin pixel if px given skin is greater than px given not skin. How about this deceptively similar but different condition? That is, p skin given x is greater than p not skin given x. While we're at it, let's throw in a couple more choices. Px given skin times p of skin is greater than px given not skin times p of not skin. Is that sufficient? How about this last one? P skin given x times px is greater than p not skin given x times px. Select the condition or conditions that you think you can use to decide whether a skin pixel is being seen given a value x. So the first one seems tempting. You have these values, why not use them directly? But note that these are just likelihoods of observing x. They are missing prior probabilities. The probability that a random pixel, regardless of its value, is a skin pixel or not is important. Take this image for example. All these pixels on the face and on the neck are skin pixels. But as you can see, this is a really small area compared to the total image area. If this is all the data we had, then the prior probability of a pixel being skin pixel would be pretty low, say around 0.2. The sum of this and the prior probability of not skin must sum to 1. So therefore, that value would be 0.8. These two values must be multiplied on the respective sides to weight the likelihoods. All of a sudden, the distinction is not as clear. Okay, so the first one is not enough. The second choice is exactly what we're after. If we find that the probability of skin given x is greater than the probability of not skin given x, then we have no reason not to believe that it is a skin pixel. Well, that was clear. Okay, the third choice is exactly the same as the first one, except we have the priors multiplied. So yes, this is a valid condition. You'll see why shortly. The last one is a little less useful. In fact, it's the same as the second form, but with p of x multiplied on both sides. Okay, if it's the same as the second, then I guess it's also valid, but not too useful.
What I'm going to do is show you, it's sort of a simple version of what's called the likelihood ratio test. And here we're basically assuming that the cost of calling a skin pixel not skin is the same as cost calling a not skin pixel skin. We can reweight these things if the costs are different. Likelihood ratio test says basically, look, it's just exactly what you think. If the probability that it's skin given the hue measurement is greater than the probability that it's not skin, what am I going to do? I'm going to call it skin. Right? That assumes that the costs are equal. So, using Bayes' rule, P of skin given x is just P of x given skin times P of skin. P of not skin given x is P of x given not skin times P of not skin. So if this quantity is greater than this whole quantity, we're going to classify x as skin. This is just a direct use of Bayes' rule. And as I said before, we would change the weights on two sides of that equation if the costs of making the mistakes were not symmetric, all right? So problem is I don't really know the prior of being skin, right? I mean, I don't know where's the prior. So the one thing I'm going to do is I'm going to assume it's a constant. I'm going to assume it has some number, right? So the prior for a whole bunch of pixels that I'm looking at that are maybe of people or in an office where there are people around, the probability that something is skin is some number. Here it's written as omega. So if you give me enough training data, that is, you pay enough undergraduates to circle all the skin areas in an image, or you do Mechanical Turk on Amazon to indicate, to have the world out there for $0.015 a click to say what's skin and what's not skin, you could estimate the prior that any given pixel is skin. So with this training data, I can also estimate that prior, and I can measure those likelihoods, right? Those are the likelihood densities, those histograms that I built. And remember, I need two histograms. I need P of X given skin, what are the hues that I get on the skin, and P of X given not skin. All right, so with that same training data that I use for estimating the prior, I can also estimate my likelihoods. All right, which means I can more or less come up with a rule. Basically, what I'm going to do is I've got my priors, I've got my likelihoods, so I can just evaluate P of X skin given X, and if it's bigger than some number, some theta, okay, I'm going to classify this thing as skin. All right, that's it. Given some new image, I want to label all my pixels. And here's a picture. This is actually a picture of Gary Bradsky, and the thing on the right is showing you the probability of something being skin. And Gary actually was using this to build a perceptual user interface where you could move your head around, and the world that you were looking at in some virtual rendering would change as you moved your head. And in fact, here's two more pictures showing you the orientation, right? So here it's pretty much straight up. Here he's turned his head. And all it's doing is tracking the skin pixels of his face. That's all. All right? And in fact, Gary made use of this in a cool little tracker. Remember we talked about mean shift tracking just recently, actually, just a couple lectures ago? Gary did sort of a different version of that called cam shift, which was maybe a little easier to implement sometimes. It's a pretty highly cited paper. And it was basically using these color distributions in order to be able to track your head and change what was rendering. In fact, the picture on here right comes from his paper where they were using the Quake engine for controlling a first-person shooter, and if you just turned your head, okay, the thing would just move with you, okay? And it was just done by tracking the skin pixels. A couple of more points about generative models. They're pretty straightforward. First of all, we've been doing the two-class case, right? You're either a skin or not skin. Well, suppose I've got a bunch of classes, C sub I, and I've got a measurement X. Which C should I choose? It's written here in green, C star. So very simply, I'm going to take the category that maximizes P of C given X. That is, which category is most likely given X? Okay, that makes some sense. Well, but I don't have that directly, so in order to do that, I use the likelihood times the, what's P of C? That's our prior. Okay, so I have to have my prior. So basically in generative models, as you add a new category, you just need to build a likelihood model and you need a prior model, and that'll allow you to compare one category to the next in deciding a new label. The other thing is, you remember before we were drawing these histograms to represent those probability distributions. Well, normally what you want is a nice continuous generative model. So what you need is a likelihood density. Okay, so you don't just have a histogram, you actually want a density. And remember, it's likelihood, so it's P of X given C, not P of C given X. That we get from Bayes' rule. All right? So typically, we represent those likelihoods using some parametric form. Here it's written as a mixture of Gaussians, right? So here, this particular class 2, you see it says P of X given C2, that's its likelihood. This is one little Gaussian lump. And we do that because we said, oh, that looks, you know, maybe most of the distribution of those pixel values is actually like that. But over here, for class 1, you see that we've got 2 humps, okay? And that's just a mixture of Gaussians. And it's not too difficult to estimate a mixture of Gaussians from a modest amount of data. One of the reasons to use these kinds of parameterized distributions is it allows you to use much less data in order to fit your density. So some of you might ask, well, wait a minute, why am I doing this whole continuous fitting? Why not just use some like k nearest neighbor or parse on window method or something else that you learned in probability class? Megan's not going to remember that question, so I'm not going to ask her to remind. So why won't you do that? Well, you might do that. If you've got a